Welcome to another tutorial on TwinCAT automation software from ControlX Engineering. Today we'll be exploring the exciting topic of motion control in TwinCAT. In industrial automation, motion control involves precisely controlling the movement of objects or loads from one position to another. In this tutorial, we'll see how we can use TwinCAT for precisely controlling the connected drives or axes programmatically from the PLC. Since motion control is a big topic to cover, this will be a multi-part series. In today's tutorial, we'll cover some theory pertaining to motion control in TwinCAT. For this, we'll continue our exploration of the Solution Explorer that we started in this Getting Started series of TwinCAT tutorials and dive into the Motion node. We'll create a new axis under the Motion node and explore its various settings and configurations. Finally, we'll run the axis in simulation mode manually from the Axis online page. Okay, we got a lot to cover, so let's get started. Let's begin by looking at the various TwinCAT 3 functions available from Beckhoff. TwinCAT extends the basic PLC components by means of these functions, which are classified into the various categories as shown. The topic of today's tutorial will be TF5000 series functions, which are for motion-related functionality. TwinCAT motion functions offer a solution for almost every automation and motion control-related task, from point-to-point, CNC, interpolated motion, coordinated motion, to robot kinematics, as well as XTS and X-planar systems, which are complex magnetically driven systems developed by Beckhoff. We will cover these advanced motion functions in future tutorials. For our introductory motion control tutorial, today we'll be focusing on NC-PTP or point-to-point motion control. Let's head over to Beckhoff's website and navigate to TF5000 motion functions as shown. This page lists all available software packages for motion control. It includes modules ranging from simple PTP or point-to-point applications to robotics and complex CNC applications. An abstraction layer to the hardware enables a very flexible control of a wide range of drive devices. TwinCAT 3 NCPTP enables point-to-point movements to be implemented in software. The motion functions are enabled by adding the required licenses. Depending on the number of axes required in your system, you may choose your licenses accordingly. For our tutorial, we will start with the basic TF5000, which gives us the ability to control up to 10 axes. The axes are represented by NC axis objects and provide a cyclic interface for the PLC. This axis object is then linked to a corresponding physical axis. Control of the connected axis can now be implemented in various configurations like position or velocity, for example. The axes are configured in TwinCAT Engineering or XAE. Let's look at the features of TF5000 function. It provides support for up to 10 axes and can be extended to a max of 255 axes if required. This function supports electrical and hydraulic servo drives, frequency converters, stepper motors, DC drives, simulation axes, and encoder axes. It has support for various fieldbus interfaces like EtherCAT, CAN Open over EtherCAT, and Circos over EtherCAT. Has standard access functions such as velocity override, master-slave coupling, and electronic gearboxes. Programming can be achieved via PLC Open compliant IEC 61131-3 function blocks. Online monitoring of all axis state variables such as set points, control values, and much more. Configuration of all axis parameters such as measurement system, drive parameters, and position controller. In addition, the NCPTP function also includes gearing, camming, superposition, flying saw, and much more. In TwinCAT, the real or physical axes are represented by axis objects, which can be considered as a digital twin of the physical axis. This results in a separation between the physical and logical axis. This allows rotary, linear, electrical, and hydraulic drives all to be programmed in the same way. In addition, the axis object can simulate an actual axis, which makes it possible to do offline program development without physical hardware, as we will see in the online segment of today's tutorial. The control of the axes can be configured in various configurations, for example, position, velocity, or torque control, and various controllers are possible. The axes are configured in TwinCAT Engineering. It has support for various encoders, such as incremental encoder, absolute encoder, digital interface to the drive, such as EtherCAT, Circos, SSI, etc. Allows online monitoring of all axis state variables, such as set point values, enables control values, etc. Configuration of all axis parameters, such as measuring system, drive parameters, and position controller. Back to TwinCAT, let's open up the Solution Explorer and navigate to the Motion node. Let's go over its various components. The SAF task directly executes commands that do not require pre-processing and handles cyclic communication with the drive devices. It handles motion commands of the motion control library, performs cyclic setpoint generation of all axes and outputs to the drives. It also handles I/O communication of the numeric controller. The block preparation task, also known as SVB task, prepares the selected commands so that they can be subsequently executed quickly in the SAF task. The SVB task is not responsible for fieldbus IO. Under image, the NC process image of the SAF task is displayed. Electronic cam plates and valve characteristic curves can be managed under tables. Since TwinCAT 3 has modular structure, this modular structure is also used for motion control. The independent objects are managed via the object node. These are, for example, collision avoidance and coordinated motion groups. And finally, the axis node stores the configuration of the various axes. In part 2 of this tutorial, we will add a simulation axis and run it first manually from the motion node and then programmatically from the PLC. So make sure you are subscribed to the channel so you don't miss out on future tutorials. In order to run the axis from the PLC, we must understand the various motion control function blocks made available through the TC2 MC2 library. But before we dive into the library, we must first understand the axis node. Let's begin by adding a new axis. Right click on axes and select add new item. The insert NC axis dialog box pops up. The default name for the new axis is axis 1. You may change the name to something more appropriate for your application. If you're adding more than one axis, you can change the value here. For our tutorial, we'll stay with a single axis. Under type, choose continuous axis and press OK. Our new axis called axis 1 has been added. Let's explore it in more detail. Double click on it to open its properties and settings. We are presented with the first tab called General. Name is the axis label we provided when we created the axis. Object ID is a unique 32-bit identification number assigned to the axis object. Type is the axis type that was selected when the axis was first created. Please note that this cannot be changed once the axis has been created. If you must change the type, you have to delete this axis and create a new one with the correct type. ID is the identification number of the axis, which is assigned consecutively. If an axis is deleted, the number becomes free again and is assigned to a new axis. The disable checkbox provides a means to disable the selected axis. Please note that this is not the same thing as a save torque off. Next is the settings tab. This is where we can link the NC axis with the hardware and PLC. Clicking on the linking buttons opens up a dialog box to select the corresponding type to link with the selected NC axis. The link to IO button will allow you to select the physical drive from the IO section of the solution tree and link with the NC axis. And the link to PLC button allows you to select the axis reference created in the PLC to link to. We will see how the linking works in the next part of this motion control tutorial. Axis type shows the type of the connected drive hardware and protocol used. For example, Circos or can open using DS402 profile, etc. Unit lets you select the physical unit of the position of the selected axis. Default setting is in millimeters. Other options to choose from are meters, degrees, etc. The display setting allows you to select the units to display in the online tab. This is merely for display purposes only and does not affect the data in the process image of the axis. The results of changing the units and display options are reflected here as a preview to show how the units for the various properties will be displayed in the other tabs. The axis cycle time and axis divider is a more advanced function for when you have multiple axes in your project. These settings allow the axis to be executed in every nth cycle of the NC SAF task with the cycle time divider. For low priority axes, this value can be set greater than 1 to reduce the system load. Increasing the divider values increases the cycle time, and updated value is displayed in milliseconds. The divider can only be increased in multiples of 2, so values like 1, 2, 4, 8, and 16 are allowed. If the divider is set to a value greater than 1, the modulo value determines in which NC cycle the axis will be processed. For multiple axes, the axes with the same modulo are processed in the same cycle. Therefore, the option can be used to evenly distribute processing load by having the different modulo values for the different axes. For example, if your divider is 8, then allowed modulo values are from 0 to 7. The parameter tab is where the various axis settings can be modified. These settings pertain to maximum limits like absolute maximum velocity, acceleration, deceleration in the selected units. Here, the reference velocity is the upper velocity limit that cannot be exceeded. It is best to set the reference velocity greater than or equal to the maximum velocity setting. The maximum values limit the axis dynamics and must be parameterized greater than or equal to the default dynamics. The default values are used if the user has not specified any input values for those parameters. We will look at the other settings in future tutorials as they are outside of the scope for today's introductory tutorial. The Dynamics tab has settings to configure the axis dynamics like acceleration, deceleration, and jerk parameters. Here, the default axis dynamics are parameterized. These default values will be used if no explicit dynamics information is provided. The dynamics data can be entered here indirectly using time for determining the acceleration and deceleration values and sliders for calculating the jerk based on desired stiffness. Alternatively, the default dynamics can be entered directly here. The Online tab is the most used tab for access control and operation. From here, we can set the enable commands manually, which allows movements to be performed on the axis. Since the setting on this page allows manual control of the axis, a mandatory warning must be mentioned about the dangers and risk of injury due to movement of the axis. So if you have a physical axis connected, you have been warned. Also, as we can see, all of the controls on this page are currently grayed out and therefore not usable. These controls will become active once the configuration has been activated using the Activate Configuration button. This is what the page will look like after activation. Let's explore some of the information on this page. This area shows the current axis position as well as the set point in the units set by the user in the settings tab that we talked about earlier. As you can see, all the units on this page are currently showing in millimeter or millimeter per minute, which is the base unit that I have selected in the settings tab. The actual position shown here is determined by the feedback device, like an encoder, used by the NC axis. The set point is the target set point specified by the NC during a move execution. Lag distance is the error in position between the nominal and actual positions. Actual velocity is derived from the actual position in real time. Set point velocity is the target velocity calculated by the NC during a move execution. Override is a user defined value set using the set button in the enabling group. Total or control output shows the total output of the NC axis to the drive that is displayed in percentage. The error text field displays the axis error code when the axis has faulted. It can be deleted by using the reset button at the bottom of the page. This area shows the axis and state information like ready, moving, not moving, or whether it's in target position, and more. The set button allows the manual control of controller enable, feed enables, and override of the axis. It also shows the enable status via the three checkboxes. These are some of the manual control settings for moving the axis. These buttons allow us to manually jog the axis. If you're using a keyboard, then the function keys F1 through F9 can also be used. F1 through F4 are for manual jog control. F5 starts the axis using the values in the target position and target velocity input fields. F6 stops the axis if moving. F8 resets the axis if faulted. And F9 is used for axis calibration. The Functions tab has additional commands for commissioning an axis. From here, different move commands like absolute move, relative move, and sequences like reversing, sinusoidal oscillations, etc. can be selected. The necessary parameters below automatically adjust to your selections. Using the start and stop buttons, the selected move command with its corresponding set points will be executed. Here we can set a value for the raw drive output. Since this value is directly returned to the drive, there might be unexpected movements and therefore this setting must be used carefully. The set actual position setting can be used to set a new value for the axis position without movement. For example, if the axis position is currently 100 and you want this position to be 0, then set 0 here and hit the set button. The set target position setting changes the target position of the axis while a move command is executing. This tab has settings for coupling two independent axes into a master-slave configuration. To do this, first select the master axis from the drop-down menu. Then select the desired coupling method from the drop-down menu. For example, linear, flying saw, etc. Afterwards, necessary parameters such as gear ratio, slope angle, etc. can be entered. The necessary parameters change depending on the coupling method selected. These buttons allow a manual means of coupling and decoupling the axis. The couple button executes the coupling between the current axis and the selected master, while the decouple button decouples them into independent axes again. And lastly, the compensation tab allows settings to trigger superimposed move commands during the travel of an axis. This can be used either for position compensation or velocity superimposition. Now that we have reviewed the main components of the motion node, let's hop onto TwinCAT and create our simulation axis and execute some move commands.
Hi, this is Andrew, and I'll be walking you through the online part of the motion control tutorial in TwinCAT. Let's begin by launching TwinCAT XAE from the icon in the system tray. We'll open our training PLC solution. As you can see, We're running the XAE on the local engineering laptop. Let's expand the motion node in the Solution Explorer and navigate to the axis item. I'm going to add a new axis, and I'll leave the default name to Axis 1. Under Type, we will go with the default type of Continuous Axis. After the selections are made, click OK to continue. We can now see our new Axis 1 has been added. This is the Settings tab that Akhil covered in his presentation earlier. These are the available axis types. For our simulation axis, we'll select Standard Mapping via Encoder and Drive. The parameter page stores all the settings for the axis. Here we can see the maximum and default values for the axis dynamics related parameters. The Online tab is where we can do manual control of the axis. It is currently grayed out because we have not activated our configuration yet. So, let's go ahead and do that. It is asking us to restart TwinCAT in run mode. I'll click OK to proceed with the activation. Our solution with the single axis has been activated and the Online tab is now active. We can see the axis ready bit is true. These checkboxes show the status of the controller and feed enables. Currently, they're all off. Let's go ahead and enable them. Click on the Set button. From here, I can either click on all the three checkboxes to fully enable the axis or just click All, which will do the same thing, and put in 100% in the override field. Now we can see all three Enable status checkboxes are checked. Our axis is fully enabled. We should now be able to manually jog the axis using the yellow jog buttons. As you can see, I'm able to jog our simulation axis in both directions by using the jog buttons. F2 and F3 are for fine movements, while F4 and F1 buttons are for coarse movements. Next, I will demonstrate the execution of move commands using target position and target velocity set points. The green F5 button executes the target move command. Let's try another position set point. You can see that during the forward movement, the has job and moving forward bits are true. The bits turn off once the movement has stopped. Let's try sending it back to 0 position with a different target velocity. Now we can see that the moving backward bit is set. Next, let's see what happens if you remove the controller enable while the axis is in motion. Here I will uncheck the controller enable. The axis faults immediately and reports the error code in the error text field. We can see that the axis ready status bit is now off to indicate a fault condition. To see what the error code means, let's navigate to Beckhoff's website and search for NC axis error codes. I'll copy the error code and search for it on this page. The NC is complaining about missing controller enable, which is what we expected. We can see the ready status bit turns off when the axis is faulted. Let's go ahead and reset the fault by clicking on the F8 or Fault Reset button. The axis fault has been reset and the ready status bit is now on. Next, let's look at the reference velocity text field. This is the same setting from the Parameter tab. Let's set the reference velocity to 100 and click on the Download button besides it. We can see it is reflected here in the parameter page under reference velocity setting. Let's see what happens if we try to set a target velocity greater than the reference velocity. As expected, the move command is rejected because our target velocity set point should not exceed the reference velocity. The target velocity must be less than the reference velocity. Now we can see it moves. Next, let's head over to the Functions tab and explore some of its features. Here we can see different move functions. Let's try relative move. Okay, the axis moved 25 millimeters. Let's try a few more times. The relative move function moves the axis relative to the current position by the specified amount. Next, let's try the reversing sequence move function. This function executes back and forth movement between two target positions. In our case, between the positions of 0 and 10 millimeters with a velocity of 2 millimeters per second. Now, I will use the set actual position function to set the current axis position to 0 millimeters. Next, I'll demonstrate the start-stop function, which moves the axis by specified amount and stops for specified time, and then repeats indefinitely until stopped. Here, I'm making it move by 10 millimeters with an idle time of 2 seconds between consecutive moves. We will explore axis coupling in a future tutorial as this requires more than one axis. Thanks for sticking around and handing off to Akil now.
Thank you, Andrew. Coming up in part 2 of this tutorial, we will review the software components available in TwinCAT, particularly the motion control library called TC2MC2. We'll look at the state diagram and also review some of the important access control functions. Later, we'll start a new PLC project, incorporate the TC2MC2 library, and explore its various functions and function blocks. Finally, all the access movements that Andrew performed manually today from the Access Online tab, we'll control them from the PLC using all the available access control function blocks. That's all for today's video. By the end of the motion control tutorials, you will be easily able to run your VFDs and servo systems from TwinCAT. In the meantime, if you have any questions, please put them in the comments below. And if you found this video helpful, then please consider subscribing so you don't miss out on future tutorials. As always, thank you for watching and keep innovating.